Hi, everybody. Today we're going to be talking a little bit about Archimedes, the method. So, as far as Archimedes, the person, he was born in 287 BC in Sicily, which is in Italy. And I know there's at least two other Archimedes presentations before this, so I apologize if this is repetitive. He was a mathematician and an inventor, and he is credited with a couple things. Number one, he discovered the relation between the surface and volume of a sphere and its circumscribing cylinder. He's known for what's referred to as the Archimedes principle, which is his formulation of a hydrostatic principle. And he is also credited with inventing a device for raising water, which is referred to as the Archimedes screw. And that is a device that is still used today in developing countries. So the story behind how we discovered the method and some of his other treatises was really interesting, and I wanted to share that with you guys. So a copy of his work was made in 1950 AD, but then it was wiped clean and made into a prayer book in 1229 AD. So that prayer book is referred to as the Archimedes palimpsest, and it contained at least 7 treatises by Archimedes. It was cataloged in 1906 and discovered to actually have lots of mathematical texts in there that were super important. And as far as I'm aware, at least 2 or 3 of them are incredibly unique, and this was the only source that we have for them. So this was a really cool discovery. And the little graphic there at the bottom is how Archimedes' work would have been taken apart and transferred into and made into a prayer book. So instead of making parchment, which would have been an expensive and lengthy process, they used old parchment. And so what they would do is they would unbind the books that had been made, and they would wipe clean all of the work that had already been on there. They would rip the pages in half, turn them sideways, write their new information. So in this case, it was a prayer book. And then they would put it back together and rebind it. And there was a really interesting TED Talk that I linked in my bibliography about this process. And from what I remember, they took like 19 or something different x-rays with different colors and different speeds of light and all sorts of crazy stuff in order to try and see what was under all this work. And so in this picture here, you can see it's a little bit bigger on the right-hand side. So on the left-hand side, the kind of sepia tone pictures, that's the actual prayer book. And then on the right-hand side, that is the work that Archimedes would have been credited with or had done. So it's kind of zoomed in here, but you can see the writing up here that he would have done, and here's a picture or a diagram and some of the notes that he would have taken. I thought that was a really, really interesting process. So the full title is called The Method of Mechanical Theorems, and it was originally a letter from Archimedes to, you'll have to pardon my pronunciation, Eratosthenes, anyway, who was the chief librarian at the Library of Alexandria. And Dr. Quinn talked about this a little bit ago in college geometry, if you're in that class. But this work, or this letter, is the first explicit use of indivisibles. So basically, tiny little chunks, like how we talk about a Riemann sum, for example, where you take smaller and smaller blocks underneath a function. And the higher number of blocks you take, the smaller those blocks will be. And then the more accurately they can give you the function. So it's named the mechanical method because it relies on the law of the lever and on the center of mass. Archimedes is credited with things like the pulley and the lever and other stuff like that, and possibly also the fulcrum. And so he kind of used those things to figure out volumes and surface area and things like that. He did not consider the method of indivisibles to be part of rigorous mathematics. He explicitly said somewhere that the treatises that he was writing and the letters that he was writing were, if they weren't formal, they weren't rigorous proofs. So basically what he would do is he would do proofs by exhaustion and say that the highest extreme wouldn't work and the lowest extreme wouldn't work. So it had to be somewhere in the middle. So his formal treatises, however, that contain the results, it wasn't included in there because he didn't consider it to be rigorous enough. So the method was a technique for weighing out different slices of an object in different ways in order to reshape them. And he would turn cylinders into spheres and cones. And since he knew the volume of those things, he was able to figure out the volume of a sphere by weighing copies of those bodies. And he used the law of the lever to determine the areas of figures from the known center of mass of other figures. And if I can get it to work. So MAA, the Mathematical Association of America, which has a group here at Sherman, if you're not aware, did this little article about Archimedes' method for computing areas and volumes. And so I thought it was a really helpful animation. But you can decide how many sections you want to sort your circle into. So I picked 16, and then it shows you how you would break up those sections into little areas that we actually know the area of. And you can also see that as you increase the amount of sections, so as you increase n, then it becomes more and more like a rectangle, and we know the area of that very well. So as n goes off to infinity, this creates more of an accurate representation, just like we talked about with the infinitesimal. So within the method of mechanical theorems, Archimedes had a couple different topics that he talked about. So we'll talk about the volume of a sphere in just a second, and we'll go through the proof of that. But he talks about the area of a parabola, and he talks about the idea of balancing the parabola with a certain triangle that was made of the same material. Then we have the surface area of a sphere. The volume of a sphere could be thought of as divided into many cones with height equal to the radius and base on the surface. So that's kind of what we looked at earlier, where we had lots of different cones that made up a sphere. And since he knew the surface area of a cone, then he could figure out the surface area and the volume of a cone. He could figure out the surface area of a sphere. And then the curvilinear shapes with rational volumes. He discovered that there are non-trivial rational relations between the volumes defined by the intersections of geometrical solids. And then the other thing he talked about, though there are many other things, was the volume V of a sphere of radius r given by V equals 4 pi r to the third all over 3. And so we'll kind of walk through this proof. I did link a video in my bibliography that has 3D models, and it kind of talks about how Archimedes would have come to this conclusion of what the volume of a sphere was. So I would highly encourage you, instead of just listening to me talk, is to go look at that video and see the 3D models, because it's definitely so much more helpful to see the actual shapes manipulated. But at least you guys can get a beginning understanding of the proof of what this would look like. And this isn't Archimedes' proof. This is a proof that somebody else has done, but it's based on his work. So it says, consider the circle in the Cartesian plane whose center is at A0 and whose radius is A. So we start with the equation of a circle. X squared plus y squared equals 2ax. And we're thinking about this circle as being a cross-section through the center of a sphere. So if we had a ball, for example, that was on the xy plane, just slicing it in half and what that would look like as a cross-section. So now we're going to look at the cross-section of a sphere formed by the plane x units to the right of the origin. So basically we're slicing the ball in a different spot this time. And the area of that cross-section is pi y squared. So we're going to rewrite formula 1, or equation 1 that we had up here, as pi x squared, plus pi y squared equals 2 pi ax. And so again, we can interpret pi x squared as the area of the cross-section of the cone generated by revolving the line y equals x around the x-axis. This is a concept that was introduced probably in either Calc 1 or Calc 3, probably Calc 3, where you would take a shape or a line and then revolve it around an axis to create a 3D shape. So back down here, consider the 2 pi ax in equation 2, this part right here, and algebraically from equation 2 to equation 3, we just multiplied by 2a on both sides. But that gives us 2a times pi x squared plus pi y squared equals 2a squared times pi x. Let's see, okay, there we go, it went away. And we see that 2a squared pi is the area of the cross-section of the cylinder, which has the same height and base as the cone. So now we have 3 circular discs whose areas are pi y squared, pi x squared, and 2a squared times pi. And these are all the intersections with the plane x units from the right of the origin, with the 3 solids of revolution described above. And they have a little illustration of the intersection of these with the xy plane. And so we have the line y equals x and the intersection point xy. And here's our sphere with the center A0. And we can kind of see how a cylinder could be created by taking this line and revolving it around this sphere that we were given. Really hard to visualize, I get it. It's helpful to look at the video, but you can kind of at least get an idea with this picture. So on the left-hand side of equation 3, the first 2 areas are added and multiplied by 2a. On the right-hand side, the third area is multiplied by x. So that's kind of just talking about the algebra that we did back there. And now consider the disks themselves as bodies of constant density. So their mass and their weight is proportional to their area. And imagine the x-axis as the arm of a balance whose fulcrum is at the origin. So we leave the disk of radius 2a where it is, x units to the right of the origin, and we move the disks of radius x and y to a point 2a units to the left of the origin, and imagine them hanging them from a point negative 2a, 0 on the balance. So this talks about the principle of moments, but they see that the combined moments of the 2 disks on the left equals the moment of the disk on the left. So the balance is at equilibrium. Basically, they created two different shapes that if they balanced out, they would be, or if they were left alone, they would be balanced. As x increases from 0 to 2a, the three cross sections go through their respective solids and fill them. So they're always in equilibrium, and so are the solids. And they talk about Democritus's form for volume of the cone, which is 1/3 pi times 2a squared times 2a. And the position of the center of gravity of the cylinder is a0. So then we get this whole big long equation, which if we solve it, drops out our equation for volume of a sphere, which is 4/3 pi a to the third.